Lecture number 2, Grain Size Analysis. Why do we care? Property of soil is greatly influenced by the size of its particles and distribution of grain size throughout the soil sample. So, size of particles, if we have coarse particles, or if we have fine particles, or if we have a combination of fine and coarse and medium size particles. So size and percentage of different particle size or distribution of grain size. These are both important because both of these will have an effect on engineering properties of soil. Distribution of grain size. So we will prepare a curve which shows us distribution of different particle sizes. And from that curve, which we call it gradation curve or distribution curve, we can find certain parameters that we will use them to classify our soil. So we will go over these later, but we will find certain parameters from the distribution curve, and then we will use these parameters to classify our soil. For most granular and cohesionless soils, distribution of grain size is determined using a sieve analysis. What is sieve analysis? It's an ASTM, American Society for Testing and Materials certified standard test method that is used to do the particle size analysis for soil samples. This test method covers the quantitative determination of the distribution of particle sizes in soil. So again, using sieve analysis, we will find the percentage of material passing through different size. So basically, we will determine percent of material with different particle size. And that's our distribution or gradation curve. As I said earlier, sieve analysis is performed on granular or cohesionless soil. Granular, cohesionless soil is when we have combination of sand and gravel. So this is done on granular soil, which is mainly gravel and sand, which are particles larger than 0.075 millimeters. So this distribution of particle sizes larger than 0.075 millimeter or particles retained on sieve number 200. So if we have a sieve number 200, this sieve has an opening size of 0.075 millimeter. Whatever stays on top of the sieve, which we call it retained on sieve, is coarse material, and materials passing through sieve number 200 is fine material. So coarse material or granular or gravel and sand are particles larger than 0.075 millimeter, and that's the sample that is used for sieve analysis. When we cannot perform a sieve analysis on a difficult and dry material, we can, instead of doing the dry sieve analysis, we can do the wet sieving. It also works when we have high fine content. It's basically washing samples with water and we refer to it as wet sieving. For materials passing through sieve number 200, so sieve number 200, if we look at it, it has opening size of this sieve is 0.075 millimeters. So materials passing through sieve number 200 are fine grained soil. If particles passed through sieve number 200, means that all particles are smaller than 0.075 millimeter, means that we have a fine grained soil. Fine grained soil, we cannot do the gradation curve or particle size analysis using sieves, because even you will see this in lab, sieve number 200 has a very small opening. So we cannot use sieves to do the particle size analysis for silt and clay. Instead, we use a test called hydrometer test. Hydrometer test determines the grain size distribution by observing the settling velocity of particles. The hydrometer measures the specific gravity of soil suspension at the center of its bulb. Again, we have another ASTM that can be used to perform hydrometer tests. This is a hydrometer, and a hydrometer generally is used to measure a specific gravity of liquids, and it can also be used to measure a specific gravity of soil suspension. So we make a soil suspension and then use hydrometer that you see in this slide to measure particles, or to do the particle size analysis. So hydrometer gives us a specific gravity of soil suspension at the center of bulb. So this is center of bulb, and then it moves based on the amount of particles that we have. Hydrometer moves. So what we do is that we measure at different times. At time t, we measure L distance that the hydrometer moved. Using time and distance, we can calculate velocity. So settling velocity is equal to distance that particles fall in time t. So at different times, we measure L, then we can calculate velocity, settling velocity, and then using that, we can calculate particle diameter using this formula. So again, for particles larger than 0.075, or this is sieve number 200 here, that has an opening of 0.075 millimeters. For materials larger than 0.075 millimeters, we perform sieve analysis test, and for materials smaller than 0.075 millimeters, we need to do the hydrometer test. And then we can make the gradation curve. We have grain diameter and percent finer or percent passing. And then we can say what percentage passed through different sieves or different opening sizes, and then we can have our gradation curve. So for this class, we will do sieve analysis in lab. Objectives of the sieve analysis are to get grain size distribution curve, which is again the curve that gives us percent finer or percent passing from different sieve sizes that we have. Then we find a median size, D50, effective size, D10, D30 and D60, and then we calculate coefficient of uniformity and coefficient of curvature. So we will go over all of this. Sieve analysis. Sieve analysis, the ASTM designation is 422, a standard test method for particle size analysis of soils. You need to select a set of sieves with different opening sizes. So as you can see here, we have sieves with different opening size. We select our sieves. Each sieve has a label on it. These are all standard sieves, and it has a sieve number and sieve opening size in millimeter and in inch and in micrometer. So we select our sieves. These are the sieve numbers and corresponding sieve opening sizes. The first thing that we need to do is to clean our sieves. We have different type of brush. The soft brush is used for cleaning the finer sieves, and the harder brush is used for sieves with larger opening size. So we need to make sure that all of our sieves are clean. Then we need to prepare our soil sample. You need to make sure that you crush your sample using a mallet, rubber mallet, before starting your test. So you prepare your soil sample, use a rubber mallet to break all the soil that are sticking together into individual particles. And then when you have your sample ready, you can start the test. The first thing that you need to do is to measure weight of empty sieves. Then after we measure weight of sieves when they're empty, we need to stack them on top of each other. So you need to make sure that coarsest sieve is on top. Then we have intermediate sieves, then our finest sieve, and then pan. So here in this example, we have sieve number 200 and sieve number 4. This is our coarsest sieve, and this is the finest sieve that we have. Then we can have the intermediate size. It can be different. It's okay. For example, we use these sizes, but it's important that we have size number 4 and number 200, because number 200, below number 200, we have fine grained soil. So sieve number 200 separates coarse grain from fine grain. And here, between number 4 and number 200 is sand, and here is gravel. So that's why number 4 and number 200 are very important for us, because it separates the amount of coarse grain from fine grain. Number 200 separates coarse material from fine material, and number 4 is the sieve that separates gravel from sand. So we measure weight of sieves when they're clean and empty, then stack them on top of each other, then measure weight of our soil sample, and then put it in coarsest sieve. So we place it here, put the cap on, place it in the shaker, and then shake our sample. After the shaking is done, then we remove all the sieves, separate all the sieves from each other carefully so we don't lose any particles, and then measure weight of each sieve with the particles retained on that sieve. So the example that you see here, these are sieves with particles retained on them. We measure weight of sieve and soil particles retained on the sieve. So let's go over an example. We start with a sample that has an original weight of 2000 grams. A dry soil sample weighing 2000 grams is brought to the soil laboratory for mechanical grain size analysis. We select our sieves. We want to make sure that we have sieve number 4 and number 200 in there. Number 4 has the opening size of 4.75 and number 200 has the opening size of 0.075 millimeter. Then measure weight of empty sieves. Then stack them on top of each other and add the 2000 soil that we have place it on the coarsest sieve and then shake our material. After we're done with shaking, then we measure weight of sieve plus soil. The difference between these two numbers gives us weight of soil retained on each sieve. So we have a sieve. We measure weight of sieve when it's empty. We have empty weight. Then we do the test. We place our soil sample, shake it, and now we have sieve with particles retained on it. We have sieve plus retained particles. So if you subtract weight of empty sieve from sieve and the retained particles, then you get weight of soil particles retained on that sieve. So for example, here in this row for 3/4 inch sieve, weight of retained is 755.1 minus 755.1. For number 4, sieve number 4 is 920.3 grams minus 612.3, which gives us 308 grams. 300 grams of our 2000 gram is retained on number 4. Then, for example, for sieve number 200, we have 356.3 minus 314.3, which gives us 42 grams. So we need to do that for all of these sieves to calculate soil weight retained on each sieve. And this is in grams. We also need to calculate mass loss to check the accuracy of our test. So how do we do that? We started our test with 2000 grams. This is the original weight of soil sample. We started with 2000 grams. When we do the test, we add all the numbers that we have in soil weight retained, and sum of these numbers is equal to 1990 grams. So this means that we lost around 10 grams, 2000. We started with 2000, but from the table we have 1990 grams, which means that we lost 10 grams of soil material while performing the test. We divide that by our original weight to calculate mass loss. So how much material did we lose while performing? So 10 grams divided by 2000 grams times 100, which gives us 0.5%. That's how much material we lost while performing the test. As long as this number or mass loss is less than 2%, the result is acceptable. If the number is higher than 2%, then the result is not acceptable and test needs to be redone. So now that we have our sieve size and sieve opening size, and we calculated weight retained, the next thing that we need to do is to calculate weight retained percentage. So here we had weight retained in grams. Now we want to calculate weight retained in percentage, which means that what percentage of material is retained on each sieve. Again, in the previous column, we retained how much in grams is retained on each sieve. Now we want to calculate what percentage of the 2000 gram is retained on each sieve. So we need to divide weight retained grams by total weight. And total weight was, when we added all of these together, we had 1990 grams. So 0 grams out of 1990 grams, 0%. For a 3/8 inch, 158 divided by 1990 grams. For number 4, 308 divided by 1990 grams times 100. This will give us 7.9%. This one 15.5%. So again, if you want to do it for sieve number 200, 42 grams out of the total weight is retained on number 200. We divide 42 by 1990 grams, multiply that number by 100, and we get that 2.1% is retained on sieve number 200. And that's weight retained in percentage. Now that we have weight retained in percentage, we need to calculate cumulative retained in percentage. What is the total material retained on top of each sieve? So on top of sieve 3/4, we have 0%. Above 3/8 inch, we have 0% plus 7.9. So here we have 0 plus 7.9. Above number 4, we have these 3 sieves. So we have 0 plus 7.9 plus 15.5. Okay, and so on. So here we have 0 plus 7.9 plus 15.5. Then here we have these 4. So 0 plus 7.9 plus 15.5 plus 30.6 and so on. So when we get to the pen, when we add all of these together, it should be 100%. That's one way for you to check your numbers. Now that we have cumulative retained, the last step is to calculate percentage passing. So we have total materials retained on each sieve in percentage. We need to calculate total materials passing is 100 minus cumulative retained. So here it's 100 minus 0, 100 minus 7.9, 100 minus 97.5, and 100 minus 0.4. And that's our table. And we use opening size. This is our vertical axis, sorry, horizontal. Opening size is our horizontal axis. And then we use percentage passing. That's our vertical axis. And we can draw our grain size distribution curve. So these are the sieves that we selected, the corresponding opening size, percentage passing from each sieve or each opening size. Data points 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 sieves that we selected.